Hello, hello, hello. Okay, let's see. Share, advance. Hello, everyone. We got plenty of time before starts, about 7, almost 8 minutes. So feel free to ask me questions if you have them. Otherwise, I'm just here early in case y'all did. Yeah, y'all can go ahead and chat me your first and last name, so I'll have that for roll sake.
I did have a quick question.
Yeah, Daniel.
With Pearson, it had mentioned on last weekend when we had the test with the conceptual 2,
Mm-hmm.
it put conceptual 3 with it as well. Is that still going to be due that weekend or is it should be due this weekend?
No, conceptual 3 is was supposed to be due last night, but I thought I changed that for your class because we missed. So I'll definitely be moving that. I'm gonna definitely have probably conceptual for chapter 3 and part 1 will probably be due Sunday, but part 2 of chapter 3 I'm gonna make due Tuesday night.
Okay, sounds good. Thank you. Just wanted to clarify before
Yeah,
you
I'm
got to
glad
work.
you asked me because I realize now I don't think I actually did change that for your class, and that would be screwed up because you didn't have enough information to do the conceptual yet. So if anybody did it, I'm probably going to give you a bonus points for doing it early. But if you didn't do it, I'm not going to mark it off, and I'm going to set the due date later.
Thank you. I appreciate it.
You're welcome. Feel free. Anybody else has questions? Feel free to ask. I'm in the process of trying to pull up my Access Pearson site so that I can see my e-text as go. I don't think I'll actually need it that much, but I want to go ahead and make sure I set those homeworks due dates correctly. So I'm going to do that real quick. Yeah, definitely had the wrong dates for chapter 3. Sorry about that, everyone. I thought I'd taken care of that, but I clearly did not. So let's see, chapter 3. Way down here at the bottom, near the bottom. Okay, chapter 3, conceptual. I'm going to make that due the 21st. Part 1, I'm going to make that due the 21st as well. And part 3, or part 2, excuse me, I'm going to move that to the 23rd.
The practice tests that you have on Canvas, do those have a due date associated with them?
Yes. So the practice tests are due on the day of the actual test that they're for. So if you don't get them done before the for the actual test, you're not going to get extra credit because that's the whole point of making them. That makes sense?
Yes, it does. Thank you.
No problem. All right. So I just reset the dates for chapter 3. I'll look and see who, if anybody, has done them already, and try to give y'all extra credit for doing them early, even though you didn't have to. So, again, I apologize for that. I did tell everybody that you're welcome to go ahead and chat me your first and last name if you haven't done so already. It looks like most of you have, but not all of you. We still got about 3 minutes before class is supposed to start. Still got about 2 minutes, as I said. Anybody has any questions, go ahead and ask me now. Just look, we still have 24 people enrolled in this class. It's crazy that I'm only getting like 17, 16 showing up. All right, down to the last minute, folks. All right, let's go ahead and get started, everyone. It's 5:30, and I'm going to start by going ahead and sharing my iPad screen. But before we do that, does anybody have any questions that they need answering? This can be questions about homeworks, practice about questions about the practice test, upcoming tests, syllabus, any of that kind of stuff. Did you post a video for the class on Monday? Uh, no, actually, I was going to, but then I didn't. Basically, I couldn't make the video because my iPad that I bought didn't work. So I'm still having problems. I just basically got it set up today. So, no, I didn't make one up, but I'll probably make one up to augment this chapter, or I might make one up to augment chapter four. I'm not sure. There's plenty of videos in the online, I mean, in the modules for this week. So hopefully that alone can get you through. Uh, we we're probably going to have to try to figure out some way to make up the day that I missed, but it'll be done by you watching a video or you doing a homework assignment or something like that. But no, I did not do a separate one. But there are plenty of videos to watch. If you're looking for something, just let me know if what you're having difficulties with, and I'll point out a specific video for you if you want. Other than that, I'll just send out an email and let everybody know, hey, such and such a video. Here's a link. Check that out. Anybody else have any questions? All right, well, let me go ahead and share my iPad screen with you folks. So this should pop up any second now. Okay. So when we spoke last time, we had gotten to the point where I had managed to show you how to add vectors using the displacement vector as a model for what addition is, meaning if you consider a trip where you're leaving your front steps, for instance, as a series of short straight trips, then each of those short straight trips has a defined displacement vector associated with it. And by necessity, if you walk from your front porch to the end of the first displacement along a straight line, then you're at the arrow of the first displacement. And then you walk on the next short straight trip. That's literally you walking from the head of the last vector to the head of the next vector. And then you keep doing that and so on and so forth. And then when all that's done, your final displacement vector from the very beginning to the very end is the sum of those individual displacement vectors. And in so doing, we learned a couple different things. I want to refresh your memory about what those things were. One of the things was that when vectors are head to tail, then the sum is a vector that points from the tail of the first to the head of the last. So, for instance, I could make a vector. Oops, I should probably put it on pen instead of dotted. So I could make a vector like this, and then say there's a vector on the end of it like this, and that's A vector and B vector. Then the sum is the resultant vector. That's the R that you'll hear me use on occasion. That vector is the resultant R, and that's equal to A plus B. Now, if instead you had given me a vector that was tail to tail, then there's a different way. I'm going to go over 4 and up 4 from this spot, and over 4 and up 4 would put me right there. So I'm going to go like this. And then I'm going to go over 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So that right there is the 1, 2, 3, 4, 5. Oh, I think I went 7. I think I went too far. Yeah, I did go just a tad too far. I'm trying to make almost exactly the same vectors as I had before. Oh, the last one was 1, 2, 3, 4, 5 and a half. Well, that's about 6 total. Yeah, 1, 2, 3, 4, 5, 6. So that is about 6 total, plus or minus a little bit. So I've now drawn sort of the equivalent vector. I let it go over a little bit of the 6 mark to make up for the difference in the two. But when they're tail to tail, what we taught you is that in the scenario that we're dealing with right now, these are vectors in just regular fields, in which case the only thing that matters is the magnitude and direction of the vector. So as long as you don't rotate them, that would be changing their direction. And as long as you don't compress them or stretch them, that would be changing their magnitude, then you're allowed to pretty much, excuse me, you're allowed to pretty much do anything else. So what we can do is we can imagine taking the vector A and sliding it along vector B. And when I do that, basically it's going to be here 1 second, then it'll be here, then it'll be here, and then finally it's going to be right here. So this is the new version of vector A. And now I can take B and slide it along A. So it's going to be here and then here and then here. And when I do that, that vector will be this. Okay, so there's the new B vector. Now, when you have the vectors tail to tail, you can now see what your job to do is. It has to match the same result that we had before, and that's pretty obvious from this what that is. But the result is that we draw from the common tail. Oops, wrong color. We draw from the common tail to the common head across the parallelogram. So the rule is when they're tail to tail, you draw a vector from the tail of the first to the head of the last. Or excuse me, when they're head to tail, you draw a vector from the tail of the first to the head of the last. When they're tail to tail, you complete the parallelogram and you draw a vector from the common tail to the common head. So that's what we were able to do. Then I was able to show you what happens when you multiply a vector by a scalar, and that allowed us to figure out what to do with subtraction. And in fact, a vector minus b vector is defined to be the a vector plus the opposite of b. When you learn this in pre-algebra, it was just a minus b equals a plus the opposite of b, and the opposite of b was defined to be the additive inverse. Additive inverse means the number that you add to another number to make it zero. So if the number was A, its additive inverse would be negative A. Or if the number is B, then its additive inverse would be negative B, because if you add B plus negative B, you get zero. Well, that's the same thing that goes on here. And we made the argument that if we took a trip 1,500 miles due east, let's say from San Francisco or something like that, then we would end up somewhere in Kansas, due east of where we left. The opposite of that trip would be basically the trip back, and that would be from that same point in Kansas back to San Diego or San Francisco, wherever we ended up going. But that would be 1,500 miles, and in that case, it would be in the westward direction instead of the eastward direction. So that was our argument that when you multiply a vector by a negative number, you reverse its direction. If that number's bigger than one, then you're going to make it longer by that factor. If that number's smaller than one, you're going to make it shorter by that factor. So, for instance, if you multiply it by 1/2, it's going to be half as long. If you multiply it by 2.5, it's going to be 2.5 times as long. If you multiply it by negative 1/2, it's not only going to be half as long, but it's also going to be backwards. And if you multiply it by negative 2.5, it's going to be 2.5 times as long, but it's also going to be backwards. So now we can see with the exact same two vectors, I'll go up 4 over 4. So I'm going to say from here to 1, 2, 3, 4, 1, 2, 3, 4. I'm going to say this vector is vector A. And now I'm going to say this vector right here is vector B. That's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Something like that. That is vector B, and I want to know A minus B. So A minus B, which is defined to be A plus the negative of B. What I'm going to do now is take my B and put the head at the opposite side and draw it like that. You see now what happens is I have A and negative B. And according to the definition, A minus B is just A plus the negative B. So now we see that the two vectors that were tail to tail are now head to tail. And the resultant, of course, of this are what we might call the difference is going to be, let's use a green color this time, I think. So I'm going to draw it from the tail of the first to the head of the last. And this would be D, meaning the difference is equal to A minus B. So that's how you do subtraction between two vectors that are already tail to tail. If we had two vectors that were head to tail, then I would go again. I'm going to try to do the same vectors. So I'm going to go up 4 and over 4. This time I'm going to go over 6. So 1, 2, 3, 4, 5, 6. There's my A. There's my B. I want A minus B. So I can go ahead and write B, negative B, by just putting the head at the opposite side. Now I see I have the two vectors that are pointing head to head. We don't have any prescription for that, but we do know we're allowed to slide vectors along. So I'm going to slide a vector along to 1, 2, 3, 4. I'm going to slide this vector right along here, and now it's there. Okay. Now, by sliding that vector, I've sort of done the same thing as completing the parallelogram. In fact, I could have completed the parallelogram, but that's not really the prescriptive method for when we're doing subtraction. So what I am going to do is I'm going to draw it because now A and negative B are actually in head to tail formation. See, I've got the head right there. I've got the tail right there. So I draw a vector from the head of, or excuse me, from the tail of the first vector to the head of the second. And which one's first and which one's second doesn't really matter because we already found out that A plus B is the same thing as B plus A. So this is our difference vector. D is equal to A minus B. So that's really the synopsis of what we did last time. Of course, we also had the whole scenario where uh, if this was vector A, then this is vector 1/2 A. And let's say this would be vector 2A. Okay. And additionally, you could say that this is vector negative 2A and that this is vector negative 1/2 A. Okay. So now we need, now that we've got all this done, we need some way of adding vectors in general other than graphically. So the method that we use is I'm going to first off draw a x and y axis. Now this extends to 3 dimensions as well, but I'm just choosing 2 right now. So there's my y-axis, and there's my x-axis like that. And if you have a vector, let's say this guy right here is vector A, and let's say the magnitude of vector A is equal to 25.0 meters per second. Meters per second is a unit for velocity, and velocity is a vector quantity, so it works. It also is a unit for speed, but speed's not a vector quantity, so this couldn't be speed, but it can be velocity. And I could say that this angle, you can roughly approximate what it is. It's up 2 and over 3. And if I did inverse tangent of 2 divided by 3, I'd find that that is 33.69 degrees. And that's what that is. And basically, I was just basing it on the first 3 boxes that I went to the right and then went up to. It almost hit right there. So that's approximately what it is. Now, how do we draw the components? Well, what the x component is supposed to be like a shadow drawn on the x-axis. So if you imagine light shining from vertically above the vector, that which is represented by this arrow, then it will cast a shadow on this x-axis that is basically the same sort of length, if you will, meaning it only goes to directly below the end of the vector. So that's supposed to line up perfectly with that. This is a sub x. And since I drew it with a vector symbol on it, that's a sub x vector. Now, this one, if we imagine casting a shadow from a horizontal light, we could actually imagine the shadow of the horizontal light extending to here, and that would be considered a sub y vector. But we're not using these guys as vectors. It's just because I showed them with the arrowhead so you'd know what they were. I'm treating them like vectors for that reason. Now, here's the big deal. Once you draw your vector in space, you've got to imagine walking from the tail of your vector to the head of your vector by taking one of two paths. First, well, you actually got to take two paths, but which one you choose first is up to you. But one needs to be parallel to the x-axis, and the other one needs to be parallel to the y-axis. It doesn't matter which one you do first; you just have to do one. So I'm going to imagine walking from the tail of the red vector to the head of the red vector by choosing those two paths. So one of them I could do is choose to go to the right first, and that's where I go. That will be my x component. And notice it pointed to the right, which is the positive x direction. So that's a positive x component. If it pointed to the left, it would be a negative x component. Now my next one is going parallel to the y-axis, and I have to go up to get to the end of the vector. So that is my y component. And notice that points up, which is the same direction as the positive y direction. So that would also be a positive component. Now I'm going to use our knowledge of trigonometry, which I know as some old horse came a hopping through our alley. That's the way I say it, but most people say so ka toa. And that means sine theta equals opposite, equals opposite over hypotenuse. Cosine theta equals adjacent over hypotenuse. And tangent theta equals opposite over adjacent, which we rarely use that to find the x or y component, but we often use it to find the angle. So what I recommend you doing at least maybe half the semester, basically until you really feel comfortable adding vectors, you should always take the time to go ahead and write what the sine of theta is. And in this case, theta, we're talking about 33.69. So the sine of 33.69 has to be the opposite over adjacent. Now, what I want to remind you is when you draw these vectors, these vector components like this, because one's parallel to the x-axis and the other one's parallel to the y-axis, they form a right angle. That right angle symbol looks like an arrowhead, therefore it's pointing to the hypotenuse. So the right angle points to the hypotenuse, so you know exactly which one's the hypotenuse. The adjacent is the one that's not the hypotenuse, but is touching the angle. So this one is actually touching the angle, so that's the adjacent. This one has to be the opposite. So trig functions are equal to ratios of lengths, uh, lengths, not links. So in this case, sine of 33.69 should equal opposite over hypotenuse, and that would be AY over 25.0 meters per second. Similarly, cosine 33.69 degrees is equal to adjacent over hypotenuse, so that one's going to be AX over 25.0 meters per second. Now, notice I haven't put any signs in here, but I specifically told you that the x component was positive and the y component was positive. And you might say, well, what if I had chosen to go the other direction first instead of, I first went from the tail parallel to the x-axis. What if I started at the tail and went parallel to the y-axis first? Well, if I did that, then what would happen is I'd go from the tail parallel to the y-axis. That gives me a positive y component, which is the same thing I got last time. Now I'm going to go parallel to the x-axis. That means I got to go this way, and that points to the right, which is the positive x-axis. So again, we found out that both components are positive. It's when you're doing this sine and cosine that you actually decide what the sign of the component is going to be, and you've got to do that. I always use the angle uh, that's less than 90 degrees and go straight from the vector to an axis. That's just a lot easier. If you go, 280 degrees, it gets really confusing to try to figure out, okay, 280 degrees, how does that work in a right triangle? It can't, right? It's just 10 degrees past 270, so it's a 10-degree angle, and then I would use the sine of 10 degree and the cosine of 10 degree and figure out whether that's giving me the y component or the x component, and figure out whether the x components are positive or negative. So in this case, we're going to go ahead and finish this one up just so you know what we got. So a sub x is going to be 25.0 meters per second. We've already defined it's going to be positive, so I'm going to put the positive there, times the cosine of 33.69 degrees. And that is 25 times cosine 33.69 gives me 20.80 meters per second positive. Actually, let me double check that because this calculator acts a little funny. So 25 times cosine parentheses 33.69 degrees. Yeah, that gave me the same thing. Now I'm going to do a sub y. That's also decided to be positive, so that's 25.0 meters per second times the sine of 33.69 degrees. That means that's going to be positive, so I'm going to say 25 times sine 33.69, close parentheses, and that gives me 13.87 meters per second. So that's how you do it. Now, one of the nice things that we can do is introduce unit vectors. Okay, so now that I know the components of this vector, I could actually write that vector A is equal to 20.8 meters per second in the x hat direction. So that X with a hat on it in the physics world and a lot of the math world, but definitely in the physics world, when you see a hat over a symbol, it often means a unit vector. Now, that unit vector is a vector that has a magnitude of 1 unit, not 1 meter per second, not 1 Newton, not 1 meter. It just has a length of 1 unit. So I use the X hat because I'm imagining a vector that is exactly 1 unit long parallel to the x-axis, so it would actually look exactly like this. That would be the x-hat vector. But we also call that the I-hat vector. You can use either one you want, but I've noticed sometimes students forget whether which one's I, which one's J, and which one's K. So I said just, don't worry about it. Just call it x-hat, y-hat, and j-hat. Similarly, I can define another unit vector called y hat, and it would be right there, but that's also called j hat. So I can continue to write A as 20.8 meters per second x hat plus 13.9 meters per second y hat. Again, that's exactly equivalent to 20.8 meters per second I hat plus 13.9 meters per second J hat. And then to save space even more, you can put this as 20.8 after a less than symbol, and then a 13.9 after a comma, and then a greater than symbol, and you could stick the units outside, or you could put the units inside if you wanted. You just have to write them twice. So I wrote it that way. So that's a lot nicer way to do it, is with that less than or greater than symbol. So that's just a whole nother way of adding them. Not only that, if you're lucky enough to get vectors in this x hat, y hat, or I hat, j hat notation, then they're just like adding like terms, because what it turns out to be when you add this vector plus this vector plus this vector plus that vector. You're basically adding the x components like that, and then add it to this guy too, and then add it to this guy as well. And you see that this is the actual x component would be from here to here. So, in other words, when I added these top two red vectors and then that third vector and that fourth vector, the result I got was just that much x. And you could do the same thing with the y. You can say, okay, well, this is the y of the first vector. This is the y of the second vector. This is the y of the third vector. And then this is the y of the fourth vector. So what we know is the actual y component is just this little guy. So what that's telling us is when you have a resultant r, which is equal to a plus b plus dot 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 for whatever number of vectors you have, then r sub x is equal to the x component of a plus the x component of b plus dot dot dot, and the y component of r is the y component of a plus the y component of b plus dot dot dot. And then of course you have the same thing for the z component. Even though I didn't choose to show you any of that, it still works out the same way. So that's how you're going to add vectors, is you're going to find the x and y components of each of the vectors, making sure you determine what their signs are, and then you're going to add all the x components to get a new x component. You're going to add all the y components to get a new y component, and remember you have to add them with their signs, so this is like adding signed numbers. And the result will be a new x component and a new y component. You can then write them on the coordinate space, or you can just record the r hat or the r vector as x component I hat plus y component j hat. But generally, I normally want you to write it in magnitude and direction notation, so I won't necessarily accept those answers. But if I do accept them, or I do tell you explicitly you can do it, that means you can do it, and that'll save you a lot of work. So now that we've talked about that, that's basically the whole crux of adding vectors. So it's now a good time for me to go ahead and add four vectors. So I've gotten some four vectors chosen already. That's what we're going to do here. So I'm going to start off by trying to draw an x-axis and a y-axis. And I'm going to try to draw it in the center of the page as best I can. It looks roughly like it's going to be, let's say here. I'm going to draw an x-axis pointing up, okay? Or excuse me, a y-axis pointing up. And now I'm going to try to draw an x-axis pointing to the right, okay? Now this is going to be my x-axis. This is going to be my y-axis. And of course the x-axis and y-axis continue beyond that. It's just these parts are the negative parts of the axes. Okay? So first off, I'm going to draw vector A. By the way, notice I put them in bold print in the top line, and I wanted to put them in bold print in those other lines because that's the way you can write a vector in typesetting, but I just never got a chance to put the vectors in boldface, so I apologize for that. It should be the A, B, C, and D after the colon should all be boldface. But I'm showing you the various ways that you can specify a vector in a magnitude and direction format. There's a bunch of different ways. The ways are including this direction is also considered north, so we normally say north is the positive y direction, and we also say it's a compass heading of 0 degrees. This one's east, and that's 90 degrees. This one's south, and that is 180 degrees. This one's west, and that is 270 degrees compass heading. So with all that known, now we can go ahead and draw these vectors. So first off, A is 7.62 newtons at 23.2 degrees. Well, that turns out to be over 7. 1, 2, 3,
Uh,
4. Yes.
Professor, I just want to check. Um, just because I know from a compass that's the zero, north would be the zero direction,
Mm-hmm.
but for calculus 2 and pre-calc 2, the x
Is
east
the zero
direction was
direction.
generally where the zero would be.
Right.
But we're not using it for this.
No, we are too. If you notice my specification of vector A, I said 7.62 at 23.2 degrees. So if I say at 23.2 degrees, but I don't say anything else, since that number is positive, we're going to imagine that being measured counterclockwise from the positive x-axis, just
Okay.
like you did in calculus and trig. And if it's negative, it's going to go clockwise.
All right.
But notice how I did that. I just called that at 23.2 degrees with no other description.
All right.
Good question. That's exactly the kind of stuff you need to think about. So first off, I'm going to draw vector A. I made these up on purpose to be 7 units to the right and then 3 units up. So 1, 2, 3, 4, 5, 6, 7, and then 3 units up. That means my A vector is supposed to be this guy. Okay. So that is vector A. Now, the way you're supposed to add vectors is ideally you'd like to have them head to tail, head to tail, head to tail. So what I can now do is draw another coordinate system right at the head of this vector. And that coordinate system would be that y-axis and this x-axis. And in this case, this is vector B, and it's 9.85 newtons at 66 degrees. Notice it says more than that. It says 66 degrees east of north, and actually that was supposed to be west of north. That's a typo. So uh, let's see. I did the exact same mistake in class. That's weird. So that's west of north. Now, what I happen to know is that happens to be 4 units up and 9 units to the right. So I'm going to do it that way. So I'll say 4 units up, 1, 2, 3, 4, and then 9 units to the left. I think I said right a second ago, but that wasn't what I meant. So 1, 2, 3, 4, 5, 6, 7, 8, 9 would be right there. So this vector is supposed to be from here all the way to that spot. So that's vector B. Okay. Now, just so we'll know what we're talking about here, this one was 23.9 or 23.2 degrees. And this one, the purple one, was 66.0 degrees. And notice I actually went west of north. That's what west of north means, meaning you take north and you go to the left a certain number of degrees. In this case, it happened to be 66. So that's vector B. Now I've got to draw another coordinate system at the head of vector B, like that. Okay. Now, this vector happens to be vector C, and it's 8.54 newtons at a compass heading of 200.6. Well, 200.6 is basically shown like this. This would be 90. This would be 180. So 90 to here. Oh, actually, I'm sorry. I've got it on this thing where it draws neater lines, and it's not doing a nice thing. So if I go to here, that's 90. If I go to here, that's 180. If I go to here, that's 270. I obviously want to go less than that. I want to go 200.6. And 200.6 is basically What's the angle there? 200.6 minus 180. 200.6 minus 180 gives me 20.6 degrees. So that's 20.6 degrees is the way I'm going. So now what I'm going to do is, now that you've seen all this, I'm going to use what I know. And in this case, I know I went left 3 and down 8. So I'm going to go left 3, that'd be 1, 2, 3, and down 8. 1, 2, 3, 4, 5, 6, 7, 8 is right here. So my vector is going to be from the head of that last one to this spot right there. And that's going to be my vector C. Okay. Now, again, I know exactly what one of these angles are, and in this case, the angle is 20.6. Okay. Now I have to do this last vector, which notice that how that one was a compass heading. That's what I use there. So now you've seen a west of north, which could also be east of west, east of north. It could be south of west, south of east, north of east, north of west. It could be west of south, east of south. All those are different ones, but just know it's the first thing is the direction you move away from the second symbol. Now we've also done a compass heading. Now I'm going to do D, which is a negative angle. So in that case, we're measuring it clockwise from the positive x-axis. So I'm going to draw another coordinate system right at the head of this guy. So there's my coordinate system in this case. In this one, I know I went down 4 and over 5, but that's the negative 38.7 degrees. But I'm going to show it to you with this. So I'm going to use a blue vector this time, and I'm going to go down 4. So that's 1, 2, 3, 4. And I'm going to go to the right 5. 1, 2, 3, 4, 5. That puts me right there. So that is my final vector that I'm adding. And what we know is this angle right here is 38.7 degrees. Okay. So I just tried to draw those vectors in different colors so they'd stand out. But vector A was the red one. Vector B was the purple one, which I could actually just use it for the vector symbol. That'd be kind of nice. And vector C was the green one. And then vector D was the blue one. Okay. But I need, for each of these, I need to compute the actual X and Y components, and I need to decide their sign. So what I'll do here is I will use different colors. I'm going to choose red to be negative, and I'm going to choose green to be positive, like a green for a stoplight, and I mean for a go on a stoplight, and red for a stop on a stoplight. And so what we see is the two x component, or the two components of vector A, is clearly positive, or excuse should say are clearly positive. So this is A sub y, this is A sub x, and they're both positive, as you can tell by the green color. Now all I have to do is I'm going to write A sub x. Again, you can take the time to write out sine first and cosine first, and then decide which one it is. I'm jumping ahead like I already know this stuff, but feel free to take your time and write out sine and cosine each first and then figure it out. AX for me is going to be, the magnitude of A was 7.62, so it's going to be 7.62. I'm going to leave the units off this time, times cosine 23.2. That's going to give me a positive, so 7.62 times cosine 23.2, close parentheses. That gives me 7.0, which probably was obvious to you guys, keeping track of the actual blocks, because clearly I moved over 7 blocks, right? Uh, Additionally, AY, that's going to be a positive as well. That's going to be 7.62 newtons times the sine of 23.2 degrees. So 7.62 times sine 23.2, close parentheses, that gives me 3.00 newtons. And that's exactly what we expect as well, because that was 3 blocks with that one. Now I'm going to do the same thing for B. We can see that vector B has a positive y component. So that's B, y, but it has a negative x component, and that is bx. So I can say bx is equal to, now what we learned earlier was that the number of blocks is really giving us this answer. So I know the number of blocks in the x case was 9, so this is going to be negative. Now the magnitude was supposed to be 9.85, and I'm going to multiply that times. Notice this case, I actually use sine to get the x component, so it's going to be the sine of 66.0 degrees, and that gives me negative 9.00 newtons for the y component. Y'all can check my work, but I'm using the results of the actual squares. Now b sub y, that's actually going to be positive. That's 9.85. Notice the y is actually touching it, so that's why I know it's cosine 66.0 degrees. And that's going to give me positive 4. So this is 4.00 newtons, like that. Now I'm going to do the same thing with the green vector. And in this case, it turns out that both components are negative. This is Cx, and it's negative. And this is Cy, and it's negative. So I can say Cx is equal to negative 8.54 times, in this case, the 20.6 is technically adjacent to the Cy, and it's opposite the Cx. You could see that if you chose to write the 20.6 here. So that's another thing you could do to help you. But in this case, I'm going to say Cx is equal to 8.54 times the sine of 20.6 degrees. And that should give me negative 3.00 newtons. Okay. Hopefully y'all are checking these things, but I'm pretty sure it should be right. This one's going to be 8.54 newtons times the cosine of 20.6 degrees. That's going to give me a negative. In this case, we actually went down 8, so it's going to be 8.00 newtons for that one. Now all I have left is the vector D, and I can see the y component is negative. So this is D sub y. And I can see the x component, on the other hand, is positive. So this is D sub x, which is positive. So now I can just write dx is equal to positive. Now the magnitude of D was 6.40, so I say 6.40 times, in this case, Notice I would have to actually write the angle over here as 38.7. Uh, I can do that. I'll explain the geometry of that in a second, but you see now that dx is an adjacent side, so that means dx is going to be given by cosine. So that's the cosine of 38.7 degrees. And that, of course, gives us positive 5.00 newtons for that one. dy, however, is negative, and that's 6.40 times the sine of 38.7. Notice I'm not using the negative in any of my trig functions. I never put negatives in my trig functions. That's just what I've learned over time is it's really easy to make careless mistakes that way. So it's best to physically figure out whether my components are positive or negative, and then physically force them to be positive or negative, and never take the sine or the cosine or the tangent of a negative number. Just always treat it positive, and it works out a little better. In this case, the y component should be 4.00, and that's going to be negative. Okay, so now what we can say is R, the resultant, which is what we're looking for. And by the way, that resultant is this vector right here. And it looks like it has no x component whatsoever. That's the vector A, that's the sum. Remember, when you do them head to tail, it's the a vector from the tail of the first to the head of the last. So that's exactly what the R vector is. But we learned that Rx is equal to AX plus BX plus CX plus DX. And if I add all those up, I'm going to get 7.00 plus negative 9.00 plus negative 3.00 plus. Now, all these units automatically were the same, so that's why I'm not choosing to write them, but you do need to be mindful of that. This x component is positive 5.00. Whoa. Therefore, 7 minus 9 is negative 2, minus 3 is negative 5, plus 5 is 0. So we got no x component. I might have said that wrong a second ago and said it wasn't any y component, but I meant x component. So this is zero point 0.0 newtons is the x component. That looks exactly like what the graphical addition is telling us. Now I'm going to do ry. That one's going to be 3.00 plus 4.00. It keeps switching to drawing with the special drawings, and that's not supposed to be doing that. So this is 4.00 plus negative 8.00 plus negative 4.00. So 3 plus 4 is 7, minus 8 is negative 1, minus 4 is negative 5. So this should be negative 5.00 newtons. And that looks exactly like what we got as well. So now the way I finish this up is, in principle, we could just say the R vector is just negative 5.00 newtons J hat. But we could also say negative 5.00 newtons y hat. All of those are correct answers, but generally speaking, if I give you the vectors in magnitude and direction notation, you're supposed to give them back to me in magnitude and direction notation. In this case, it's really trivial to do that. That's the downside of this particular example I made up. But what I would do is draw an axis again with your x and y exactly parallel to the original ones. And now I'm going to draw a vector downward and say that its magnitude is 5.00 newtons. And that tells me that the actual vector r is equal to 5.00 newtons, and it's at negative 90.0 degrees. Or you could also say it's at positive 270 degrees. Or you could say it's 5.00 newtons at, in this case, we could say, uh, let's say south. Or you could say 5.00 newtons at 90 degrees south of west. So all those are different ways. It would be a little less trivial if I didn't have a vector that ended up not having a y component. But what you would do if that was the case is you first use the Pythagorean theorem to find out what the magnitude is. You're going to take the x component, square it, take the y component, square it. That means if either one's negative, it's just going to become positive because the square of a negative number is positive. You're going to add those two squares, take the square root, take the positive square root specifically, and that'll be the magnitude. And then you can take the y component divided by the x component, again, treating them both as positive, take the inverse tangent of that, and that'll give you a angle in degrees. So you would then draw where that angle is on your triangle and go from there. Ian asks, wait, so I'm confused by the degrees on labeled on the axes. Are they not being used for this problem? If it is directly downward, wouldn't it be 180 degrees? Oh, yes, absolutely. That would also be 180 degrees. Thank you. You could also write it as 5 newtons at 180 degrees. But if I said at 180 degrees, I'd have to call it at compass heading 180. Does that make sense, Ian? So that's the way we go about adding vectors. Does anybody have any questions on that? So notice the big trick is sometimes you have to figure out exactly what I mean when I say something like 66 degrees west of north or 15 degrees east of south or something like that. Our compass heading of 212 degrees or due east or due south or something like that. In fact, if your book or me just says northeast, then that means 45 degrees, which is the same thing as 45 degrees from your calculus and trigonometry class. But it could also mean 45 degrees north of east, which also means 45 degrees east of north, so on and so forth. But that's what northeast means. And northwest would be again 45 degrees from the north axis and from the west axis. So just remember when they combine two directions like that, if they don't give you an angle, you can interpret that to be exactly 45 degrees. If they say north northeast, then that's half of 45 degrees closer to north because they said north twice. So that'd be 22.5 degrees east of north. That's what north northeast would be. If you wanted to say east northeast, then it'd be 22.5 degrees east of north. A little weird stuff like that. I try to avoid doing those double ones where you go north northeast or east northeast or anything like that, but I will do east of north and west of south and all that good, or excuse me, yeah, west of south and all that kind of stuff. Anybody have any questions on that? All right. Well, now we're going to start the problem of solving projectiles. So what I'm going to do is just imagine a projectile. So I'm going to go ahead and draw an axis here. So here is my y-axis and here is my x-axis. Actually, I'm going to draw my x-axis to go a little further. That looks pretty good. That's my x. That's my y. Now, no matter what, you're almost always going to have to break down your projectile velocity in terms of x component and y component. Even if they don't give you the velocity, you're going to have to assume the initial velocity is v0 and that it's at an angle theta. So What's often done is you just draw a vector like this, and I'll say this is at 60 degrees, and I'll say this is 40 meters per second is my initial velocity. So what's going to happen with this is this projectile is going to be fired and it's going to land some distance away. That distance is called the range, and it's given the symbol r, and we want to find that. However, it's also going to have a final velocity vf that we'll want to find, and it's also going to have a ht, which I call t hang time for how long it's in the air. That's another one I want to find. The last parameter that it's going to have is something called h max, which is the max height it reaches, and that's going to be something I want to work out. Okay. Now I'm going to write down what I know from this drawing, and what I know from this drawing is V0 is equal to 40.0 meters per second. I'm going to treat the 60 as 60.0 degrees. So I'll say also that theta is equal to 60.0 degrees. I'm going to say I would like to know R, H max, uh, T hang time, V final, all those things I want to know. Now, the big trick is if you look in your book, there's this nice figure that has a red ball and a yellow ball. And what's going on there is it's in a really dark room. The red ball and the yellow ball are both at exactly the same height. And when you push a button, instantly the red ball is going to be dropped, but at the same time, the yellow ball is going to be punched to the right, but just to the right, not upward, not downward at all, just purely to the right. And what you'll see is that they're then, since it's in a dark room, they're going to have strobe lights flash, and they're going to flash like every hundredth of a second or something like that. So it's going to leave an image of a red ball and a white ball, then a red ball and a white ball, or a yellow ball, excuse me, red ball and a yellow ball, red ball and a yellow ball, red ball and a yellow ball. And what you're realizing is that the red ball falls at the exact same rate as the yellow ball. That's the key to understanding projectile motion. You treat the two motions completely separately. The vertical motion does its own thing based on gravitational acceleration, slowing it down by 9.8 meters per second every second. And meanwhile, the horizontal velocity just chucks along at the same horizontal velocity through the whole period because we're ignoring air resistance. If you had actually taken into account air resistance, then the acceleration in the y direction wouldn't be downward 9.80. It'd be something different from the air resistance. And the air resistance in the x direction would be not zero. But in these problems, and essentially all of them that we're going to work with projectiles, we're not going to have any air resistance brought in. Okay? So if we look at this, we can figure out that the velocity in the x direction would be v0 cosine theta. Now, in this case, for projectiles, because you're always measuring the angle between 0 and 90 degrees, then cosine will always give the x component and sine will always give the y component. That was not the case when we were adding vectors, so you got to pay attention to that. Sometimes sine will give you the x component, sometimes sine will give you the y component. Same thing with cosine. But when you're doing projectile motion, v0 cosine theta is automatically going to be the x component. And I'm going to take 40 and multiply it by the cosine of 60. And that gives me 20, which duh. So that's 20.0 meters per second. V0y is going to be V0 times the sine of theta. So I'm going to say 40 times sine, parentheses, 60, close parentheses, and that's going to give me 34.64. Notice I'm carrying one extra sig fig. because I'm going to use these numbers over and over again. I don't want to round it and then round it and then round it. So we always carry at least one extra sig fig. So I now have that. Now we've got two problems going on with projectile motion. The first problem is I'm just double checking my watch. We start at 5:20 and we go to what 6:40?
650.
6:50. Thank you. Ooh, I got so many classes I get mixed up. So yeah. All right. So we've got two problems going on. One of the problems is a ball rolling to the right at a constant velocity of 20 meters per second. That's an easy one. We just know x is going to be uh, 20 meters per second times time. That's just always the x position. The y position, however, is going to be going 34.64 meters per second up. So after 1 second, 9.80 meters per second will be subtracted from that. After 2, 19.6 will be subtracted from that. After 3, 29.4, so on and so forth. So those are two entirely separate motions. So first off, what I want to do is figure out, let's say, h max. Well, H max is vertical motion. So really what happens is when we get to that H max spot, I think it's obvious that the velocity must be purely in the x direction. Because if it had an upward velocity, then it's going to go higher sometime later. So that can't be it because we're saying this is the highest point of the projectile. If it had a negative component of vertical component of velocity, then it would have came from a place that was higher before. So again, that's not consistent with being the highest place. So we know that the y component of velocity is equal to 0. So I'll say this implies Vy equals 0. And we know Vy, or the y motion, is controlled by constant acceleration. So all our kinematic equations are fine. So I could, for instance, find the time there, or I could just find the distance traveled. I'm going to choose to find the distance traveled. So I'm going to say Vy squared is equal to V0y squared plus 2ay times y minus y0. Notice the y on the a is a subscript, just like it is on the v's and the v0s. So this is just the v squared equals v0 squared plus 2ax, except I've written it for y. The initial y position, which you can always make it 0, I did make it 0, as you can see, it left from the origin, so I can get rid of that. The final y velocity is going to be 0, so I'm going to say 0 squared is equal to the initial y velocity is 34.64 meters per second, and that's going to be squared plus 2 times negative 9.80 meters per second every second times just plain h max. Remember, at that point, y is h max, so we can get h max is equal to 34.64 squared. That gives me 1,199.
Really quick, can you go back to where you got the 34.64? Or was that
Yes.
given?
Yes. I had to take the 40 meters per second and multiply it by the sine of 60 degrees. Do you understand why that's the case? Okay. Let me
No.
draw that. That's cool. That's no problem. So this right here is 60 degrees. This right here is 40.0 meters per second. So this is my V0x, and this is my V0y. Sine 60.0 degrees is equal to V0y over 40.0 meters per second.
That makes more sense. Thank you.
No problem. So yeah, take your time. Do this every time. Go ahead and write out what sine and cosine are. And then use those to solve for v0x, v0y, and of course remember your signs, even though they're always going to be positive of projectile motion. Now, back to this, we got the square of 34.64 was 1199.9, a buttload of numbers, and then that's going to be divided by 19.60. Now this one was 3 sig figs, and these are 3 sig figs. So those are not real, and that's not real. You can see that the units work out to be meters squared per second squared divided by meters per second squared, which just gives me meters. So I'm going to take 1199.29 and divide it by 19.60, and that's going to give me 61.22 meters as H max. Any questions on that one?
I have a question
Yes.
on when getting H max, the second term after the 34.64 meters second
Mm-hmm.
squared. Why is negative 9.80 meters a second multiplied by 2?
Okay, so the equation that I derived when we did kinematics was v
Oh, okay,
squared
so
equals v0 squared plus 2a x minus x0. So this is that same equation, but the acceleration is in the downward direction. That's why we called it negative 9.80, and it's due to gravity, so it's 9.80. Does that make sense?
yes, I didn't see the equation written right above it. That's
Oh,
my
okay.
bad.
No problem. That makes more sense. I was like, oh, crap. I don't know where you got, how we got confused on that one, but now I got you. So that's it. Now we could have first found the time and did that. That would be fine. That would be the time of H max or something like that. A way you could have done that is you could have used the equation V equals V0 plus AT, which is another kinematic equation. And if you put 0 as the final velocity and 34, oops, that's supposed to be 34.64 meters per second plus negative 9.80 meters per second squared times t, then you'd get t is equal to 34.64 divided by 9.80, and that give you 3.535 seconds, and that's t h max. So that's the time required to get to that peak. Now, that also, by symmetry, looks like it should be half of t hang time, and we'll be able to check that later. Now, if we wanted to start working at stuff at the other end, what we might want to do is say, okay, well, when the y coordinate reaches 0, it's either going to be where I fired it from or it's going to be hitting the ground. So that's one way that I can find out how long it will be in the air if I can find an equation between y, v0, and t. And that's just our 1 half at squared equation. So I'm going to say y is equal to 1 half a sub y t squared plus v0 sub y t plus y0. But remember, we already decided that it left from the origin, so y0 is 0. Now I'm going to put 0 in for the final position. I'm going to put 1 half of negative 9.80 meters per second every second times t squared plus v0y is the 34.64. Again, carrying one extra digit, meters per second times t. Now, normally this would be scary because you'd have to use the quadratic formula, but since we have y0, 0 and y is 0, it's only, there's a t in both terms, so I can actually factor out the t, and I'll get 0 is equal to t times negative 4.90 meters per second times t plus 34.64 meters per second. And this is true for t equals 0 or for t equals 34.64 meters per second divided by negative 4, or excuse me, positive 4.900 meters per second per second. Now, you can see that that's clearly going to be twice as big as TH max that we did before, but here's the proof. I'm going to do 34.64 divided by 4.90, and that gives me 7.069 seconds is equal to T hang time. And this is just like hang time, like we talked about with regards to, or like we talk about with regards to college and NFL football. You know, they want a punter to kick the ball to be in the air as long as possible on most punts. So that's what we're talking about. It's going to be in the air 7.069 seconds. That's pretty good. And of course, we did shoot it at 60 degrees, so that kind of matters. Now that we have that time, we could use that time to calculate exactly how far it's going to go to the right, because the equation for x is that, let me write this in blue like I was doing. The equation for x, like I told you, is x0 plus v0x times t. There's no acceleration. This is also the definition of average velocity, but since it's a constant velocity, the average velocity is the same thing. So with this in mind, I can put in r, the range, is equal to 0 meters because the x0 is 0, plus v0x, which is 20.00 meters per second, times the time, which is 7.069 seconds. That gives me 141.4 meters equals the range. So we see in this case that the range is 141.4 meters. Now the final velocity is given by, or at least the y component of the final velocity, Vy is equal to V0y plus a sub yt is one of the equations we can solve. And what I want to do is figure out what the velocity is just before it hits the ground. So I'm going to plug in T hang time, and I'm going to say Vy is equal to 34.64 meters per second plus negative 9.800 meters per second times T hang time, which is 7.069 seconds. And what that's going to give me is 34.64. You probably can guess it already. Minus 9.8 times 7.069. And that gives me negative 34.64 meters per second. So the vertical component of velocity when it leaves is 34.64, and since it's landing at exactly the same height, its final velocity is 34.64 downward. So I can now figure out what the final velocity is. The x component is still going to be 20.0 meters per second, but the y component is going to be 34.64 meters per second downward. So this is like the vector stuff I was telling you earlier that we have to do for the final vector when we add them. Is we've got two components and I've got to figure out the magnitude and direction. So in this case, I'm going to say the final velocity is this vector, v final, and I'm going to call this angle phi. So v final is equal to the square root of 20.00 meters per second quantity squared plus negative 34.64 meters per second quantity squared square root, you can probably figure out that this is going to come out to be 40.00 meters per second, which is exactly right. And you could probably see that phi is going to be the inverse tangent of 34.64. Notice I left off the actual sign and 20.00. And lo and behold, this is going to give you 60.0 degrees. So the final velocity, VF, is equal to 40.0 meters per second at negative 60.0 degrees. And that is a typical projectile motion problem. Now, I will recommend you go and look at all my other projectile motion problems or look at several of them on my YouTube channel. I've got several links in our week 4 module. I think I might even have a couple links in our week 3 module. But check those out. This is a really good, robust example of how to calculate problems and how to solve problems of projectile. So I'm going to wait for the last person here to leave, but you guys are free to go. Make sure you chat me your first and last name if you haven't already. We've got a little break before our next online and face-to-face test occurs, but you do have some homework due, so make sure you all work on that this weekend. Have a good one, everybody. Thank you, Daniel.
Hey, Professor.
Yes.
I just wanted to know if you had seen possibly my email, or maybe I formatted it wrong, but I sent you an email a few days ago, and then I followed up with a text message today.
Okay. I did see the text message, but I haven't. Ah, gotcha.
Okay, then you can ignore the email.
Gotcha. Yeah, I think I see that this was the one I saw. Let me double check. Oh yeah, yeah, it was you. Gotcha. I didn't see a name in it, but I see it. You just wrote it so long. Yeah, so I'm going to do that. I assumed you missed the actual test, or you just missed the other part.
The what?
Did you miss the practice test, or did you miss the online test too?
I missed both,
Okay,
actually.
so I can open that back up for you, but there's going to be a deduction in points. But I'll talk to you about that. I'll follow up with you via text message in a few.
Hey, that's no problem. A deduction's much better than 0 points, of
Yeah,
course. So.
I'm going to do that for everybody. I did have one person in my face-to-face class missed it. I normally take off 15 points, something somewhere around there. So, but I'll give you at least till Sunday of this week to do it. And if anybody else, of course, missed that test, I'm going to open it up for them as well. And you'll have till Sunday at 11:59 p.m. to do it. I'm going to open up the practice test too, just for you guys. And of course, then you'll have a chance to do the practice test too to prepare.
Okay, thank you, Mr. Younger.
You're welcome. See you, Ian. Sorry you missed it, bud. Anybody else have any questions? How about you, Zach? You got any questions? All right, that's it. So it looks like we can stop sharing and we're done here. So thanks for coming, everybody. Bye bye.